Next theorem. Next theorem states that if you have parallel lines, 3 or more, that these parallel lines, if they intersect with transversal, will always cut off other lines proportionally. And that's what I tried to get at with when we discussed the triangle proportionality theorem, is to go ahead and cover this in general. Not only with triangles. With triangles we had the triangle, we had one line parallel to another, and it cut off these pieces proportionally. And we can extend that to all parallel lines. Anytime you're dealing with parallel lines, you can take the lines on your paper as an example, and you have transversals. These transversals will have proportional pieces. Like if this was, let's call it ABC, DE, and F. And you need to find any of these pieces. A over D is equal to B over E. B over E is equal to C over F. C over B, or C is to B as F is to E. You could set up that proportion. A over C, or A is to C as D is to F. You could set up that proportion. But anytime you have parallel lines, and that goes for the rest of geometry, anytime you see parallel lines, you have proportional pieces. Parallel lines cut off their transversals into proportional pieces. Real estate says frontage is the measure of a property's border or boundary that runs along the side of a particular feature, such as a street, lake, ocean, river. You might have heard your parents talk about road frontage. When you have land, that land is worth more if it has frontage. You really don't want, if this is your road, you really don't want land that does something like this and it blossoms way back here and you've got just a tiny bit of road frontage. Because that means somebody else owns all this. But that's what frontage is it's a boundary between your land and either a road, it could be a lake, a river, whatever. That's your frontage. So it says find the ocean frontage for lot A to the nearest tenth of 100, or tenth of a yard, tenth of 100. You have Ocean Drive here, and then you have lot A and lot B. Ocean Drive has 58 yards of road frontage. Lot B has only 42 yards of road frontage. Lot B has 60 yards of ocean frontage, and we want to know how much ocean frontage that Lot A has. Notice the parallel lines. Anytime you have parallel lines, it's going to cut things off into proportional pieces. So that means that 42 yards, the 42 yards in Lot B is to 60 yards of ocean frontage, the same way as 58 yards of Lot A is to how much ocean frontage. It's proportional. It's going to cut it off into proportional pieces. You don't have to do it like this. If you want to use scale factors, that's fine too. You can figure out 42 times what number gives me 60 and use it as a scale factor, and then take that 58 and multiply it by the same number, and that would give you your frontage there. This is usually just the easiest way. Shortcut, multiply 60 and 58. Divide your answer by 42. Does anybody have X for me? 82.9. So it's about, right? So X is about 82.9 yards of ocean frontage. And let's try it the other way. Just to keep you up to date on your scale factors here, make sure you know what's going on. If I want to know what I multiply 42 by to give me 60, that means I do 60 divided by 42. So my scale factor there is about 1.42. It's about 1.42 times bigger. So multiply that same by 58, and you get that same 82.8 something, 82.85, which does round up to 82.9. This next theorem follows directly along with what we just did. If you understood that theorem, then this theorem should make sense. Is if you have parallel lines in that same scenario, we know that these pieces will be proportional. Well, this says if you've got parallel lines and they cut off congruent segments. Again, keep in mind these are proportional. You have proportional pieces. If these are in ratio of 1 to 1, that's what congruent means. The ratio of this size, or this length to this length is a 1 to 1 ratio. What's going to be the proportion over here? 1 to 1. Does it mean that these are the same? No. No. It means that if it cuts it off, if it cuts congruent pieces off on one side, that means that every transversal that you draw, those same parallel lines will cut off congruent pieces. This is a prime example of your paper, okay? Because you know that the distance between lines on your paper, unless you buy from some discount store, the distance between the lines on your paper probably the same, right? So if you drew any line down your paper, that means the distance between, or the length of those lines, any two portions of those lines will always be the same. Okay, next problem. Notice you have parallel lines. Well, I assume they're parallel. They don't tell us. Let me tell you that. You have parallel lines. Let's say those are parallel. And I noticed something. On this transversal here, it cuts off equal pieces. If it cuts off equal pieces here and here, that means that these two pieces must also be equal. They're proportional. Parallel lines indicate proportionality. If those two pieces are going to be congruent, then any pieces of any line transversal that's drawn there will also be congruent. So how do we figure out x and y? Well, our x values or our x equations must be the same, or expressions. 6x minus 5 has to equal 4x plus 3. Okay, let's solve the equation in our head. Morgan, move my x's to the left. How many do I now have? Thank you. Move my numbers to the right. How many do I have? So x must be done. So if x is 4, we always plug back in. That's 24 minus 5, which gives you 19. This is 16 plus 3, which is also 19. It checks out. Okay, it's equal pieces. Do the same thing for my y's, and we'll solve that in our head as well. 3y plus 8 must equal 5y minus 7. Move all my y's. In this case, I move them to the right. Trevor, how many do I have? And what's it going to equal to as you move the 7? Careful, plus. And y must be 7.5. Plug that in. 3 7.5s is 22.5 plus 8 is 30.5. 5 7.5s is 37.5 minus 7 is also 30.5. So you see that again, that's a picture of the theorem we just covered. Anytime you have equal pieces cut off in one line, it'll be equal pieces cut off in all lines. Okay, next problem. This actually goes back, and it's a picture of something we did previously. This, I believe, would be a mid-segment problem. But anytime, again, you have parallel lines, and you can imagine a third parallel line right here if you'd like to, just to where you can apply it to all cases. If you have equal pieces here, and I do know that these lines have to be parallel because notice these are called corresponding angles. They're the same. They're congruent, so that forces these lines to be parallel. So if you have parallel lines, and if you have equal segments here, then you will also have equal segments here. Move the 2x, set them equal to each other, move the 2x over here, move the 5 over here, you'll get x is 6. You can plug that in, that'll be a 13. This will also be a 13. And you see the similar triangle. You see how that relates, hopefully, to the similar triangles. Those two triangles there would be similar by, you could say by angle, because I see that they share an angle. You could say that those two triangles are similar by side angle side, because this is 13, the whole thing is 26. That's a scale factor of 2. This is one tick mark, and since this is one tick mark, that means the whole thing is double it. So since you have that scale factor of 2 for both of those, and they share that common angle, either by side angle side they're similar, or by angle they would be similar, you could go either direction there. Don't write all this down yet. I'm going to give you an easy way to remember it. Okay, these next three theorems states that if two triangles are similar, they all start out, if two triangles are similar, then this is true. If two triangles are similar, then their corresponding altitudes are proportional. If two triangles are similar, their corresponding angle bisectors are proportional. If two triangles are similar, the length of their corresponding medians are proportional. So in a nutshell, let's write it like this. If you have similar triangles, we've already said the sides are proportional. We've already said their perimeters are proportional. This new thing says that their altitudes. If you don't know what an altitude is, put height next to it in parentheses. An altitude is simply a height. We know their altitudes are proportional. We know their medians are proportional. We know their angle bisectors are proportional. I believe that their perpendicular bisectors would be also proportional. In a nutshell, everything is pretty much proportional. When two triangles are similar, pretty much every piece, no matter whether it be an angle bisector, if you draw two angle bisectors that correspond, now these have to be the corresponding angle bisectors. It can't be, let me show you what I mean by that. If you have two triangles that are similar, let's say this is triangle A, B, C, and let me draw a small version of it, and we'll call it RST. And if you know that triangle ABC is similar to SRT, I kind of wrote those in the wrong order. If I know that that's true, and I draw this angle bisector, an angle bisector cuts an angle in two equal pieces. That angle bisector will be proportional, and what I mean by proportional is there's going to be a scale factor here, and since it, from here to here, since it shrinks it, let's say we have a scale factor of like 0.4. It's 40% of what it was before. It shrinks it down to 40%. That means that this angle bisector will be 40% of this angle bisector. But what I'm trying to get at, it can't be this angle bisector and this angle bisector. It must be the corresponding angle bisectors. It must be the one that comes from angle A and angle S, or the one that comes from angle B and angle R. Corresponding angle bisectors are the same. Corresponding perpendicular bisectors, that's not a theorem, but I'm sure it is. Corresponding medians would be the same. If you don't remember what a median is, a median goes from an angle to the middle. We talked about medians when we did those points of concurrency. So if I remember where the three medians cross in a triangle. Center of balance or the centroid. That's exactly right. The medians crossed at the center of balance. So we know that all these pieces, if two triangles are similar, everything's proportional, pretty much. In this problem, it says that ABC and FDG are similar. And notice what they give you. They give you an angle bisector in this case. How do I know it's an angle bisector? Because that and that's the same. Because that and that's the same. I do know that angle A and angle F correspond. Now, question before, this is kind of extra information, but they put one tick mark here, and I noticed they put two tick marks here. Could they have just simply put one tick mark here and said that those are going to be the same as these as well? Yes. I know that all four of those pieces are going to be the same for this reason. If two shapes are similar, corresponding angles must be congruent. So if angle A is a 30-degree angle, then angle F has to be a 30-degree angle. If angle A is 60, angle F is 60. So if you have an angle bisector, if this was 60, then this has to be 30 and 30. Then that means this would be 60, and that has to be 30 and 30. Really, they didn't need two tick marks over there. They could have used one because all those little pieces would be the same. So we have we have the similarity here, then we have a scale factor. Let's do it this way, Thaxton. From 12 to 15, I want a scale factor. It needs to be probably 1 point something because I know it's not double. 2 times 12 is 24. That's too big. So the scale factor should be 1.25. That is the scale factor from the small triangle to the large triangle. She found that by doing 15 divided by 12. That's 1 1/4 or 1.25. So to find out, this is an angle bisector. It corresponds with this angle bisector. One way of doing it, take that 8, multiply by 1.25, and I believe you get 10. Done. The other way of doing it, since you have proportions, I'm drilling, is what I'm trying to do over and over. You can work it either way. You could say that 12 corresponds with 15 the same way that 8 corresponds with x. Cross multiply, divide by 12, and you get x equals 10. You get the exact same answer either way. Next problem. Again, if two triangles are similar, which they don't tell us here, they don't tell us, but we know that they are similar. Because this angle is equal to this angle is equal to this angle, so therefore by angle, these two triangles are definitely similar. Since they are similar, from what I just told you, that last theorem, everything about them will be proportional. So not only are the side lengths proportional, but in this case also the altitudes. Those are heights. Okay, they go from the top point, which this one's upside down. They go from the top point straight down to the base at a perpendicular height or at a perpendicular line. So that's how tall these are. So one way of doing it is find a scale factor. Let's go backwards this time. Let's shrink it from 20 to 15. Cat, see if you can find my scale factor there. What number, when multiplied by 20, will shrink it down to 15? It should be point something, 0 point something. .75, good. So to go from the big shape to the smallest shape, I'm multiplying by .75 to shrink it. It is now 75% of what it started at. So if I want to shrink that with .75, since everything's proportional, simply multiply this by .75, which is 3/4. You might can do it in your head now. Since this is 3/4, take 3/4 of this. 1/4 of 16 is 4. 3/4, therefore, would be 3 of those, or 12. Or again, you can set up the proportion. 20 is to 15 as 16 is to x. You can do it either way. Let's not work this one, but let's just talk about it. Colby TP. Stands for toilet paper, but that's beside the point. TP there, line TP. Is it an angle bisector? Is it a perpendicular bisector? Is it a median? Is it what is it? It is a median. A median goes from an angle to the middle. Okay? So this is a median, and I know since these are similar that also the medians will be proportional. You could do 9 to 13.5. I think that's a 1.5 scale factor. Multiply this 3 by the same thing, and you get 4.5. So everything's proportional. Next theorem, and I think we have 2 more. We might finish. I say we're going to finish. I think we will. The triangle angle bisector theorem. Now, in this one, we're not dealing with 2 different triangles. 2 separate triangles, I should say. We're dealing with 2 triangles that are within a triangle. And this is actually, out of this chapter, this is probably the one that is most commonly forgotten, this theorem. If you have a triangle and you draw an angle bisector inside that triangle, that angle bisector actually cuts this triangle into proportional pieces. Let me show you what I mean by that. When you draw this angle bisector, it cuts this into 2 pieces, a side and a bottom, which is actually proportional to this side and this bottom. We can't say the same thing about perpendicular bisectors. We can't say the same thing about altitudes and all those others. But this does happen anytime you have an angle bisector. So what we mean here, ABCD, the ratio of A to B is the same as the ratio of C to D. So you can actually, anytime you have an angle bisector, you have proportional pieces. Side to bottom is equal to side to bottom. They're in ratio of each other. They're in proportion of each other. Here's an example, and it got cut off, but this is an angle bisector. It cuts that angle perfectly in half. Actually, hang on. I think, yeah, let's do the simpler one first. That was a little bit more complex. This one's pretty easy. Anytime you have an angle bisector, it cuts your triangle into 2 proportional, I'm not going to say really halves because it doesn't have it, but it cuts your triangle into 2 proportional sections, which means that X corresponds with 4. The side of that angle bisected triangle, the side to the bottom, is the same proportion as the side to the bottom. Side to bottom, side to bottom. And that only happens when you have angle bisectors. X is to 4 as 13 is to 6. Now, could I use scale factors there too? Yeah. From 6 to 13, you could check the scale factor there. It's going to be like 2 point something because 6 times 2 is 12, so it has to be bigger. So you could do 6 times 2 point something, find that scale factor, multiply 4 by the same scale factor, you're going to get the side there. But let's work it this way. X is to 4 as 13 is to 6. 4 times 13 gives me 52. I've got to divide that by 6, which gives me 8.6 repeating, correct? Which rounds up to 8.7. So my side length there, 8.7. Check me the other way. You can do 13 divided by 6. take that answer, multiply it by 4. Once you get that scale factor, it should be the same answer. And I hate that I had these switched because this one is a good bit tougher than that one. Have the same scenario. You've got 6 goes with x. The side length with that bottom portion. 6 corresponds with x the same way that 14 corresponds with, careful. Does anybody know? Say again. 18 minus x. The side corresponds with that portion of the bottom the same way as this side corresponds with just this portion of the bottom. We don't know what this is. We know the whole thing is 18. We know that this small portion is x, so this portion will be 18 minus whatever this is. There's your proportion. To get rid of fractions, we're going to multiply by 18 minus x. To get rid of this fraction, we're going to multiply by x. So you have 108 minus 6x is equal to 14x. Take all our x's, move them to the right side. Taylor, how many x's do I now have? So I have 20x, and it doesn't matter really what side you write it on. 20x equals 108. Divide both sides by 20, and you get 5 and 8/20, which is 5.4, 5 and 4/10. Those. Last one of these, and then we'll go on to the last topic in the chapter. Let's not work, well, yeah, we might want to work it again. 14 corresponds with x. The side corresponds with the bottom. Again, only with angle bisectors. The side corresponds with the bottom the same way as the other side corresponds with the other bottom. 11 corresponds with n. Help me out. I need to know the length here. 14 goes with x. 11 goes with whatever this is. If the whole thing is 20, this portion over here is x. How do I find this portion in? Good. And if you don't understand that, guys, make it real. Put some numbers in for x and just ask yourself, how would I work it if this was 12? To find this, wouldn't you take this whole 20 and subtract the 12 away from it? Or if this portion was 10, wouldn't you take the whole 20 and take this 10 away, and that would give you 20 minus 10 or 10 here? So like he said, you would subtract 20 minus the whole. The whole minus that small portion. I believe that's called the segment addition postulate, if you go back to chapter 1-2, whenever we discussed that. To get rid of this x, we multiply. To get rid of this 20 minus x, since it's being divided, we also multiply. It gives you 280 minus 14x equals 11x. Help me, Garrett. How am I going to move the 14x to this side? So we have a total of 25, Garrett. Good job. And we have 280 left here. Last step, divide by 25, and I think we have quarters into $2.80, right? There's 4 quarters in every dollar. I believe that would be 8, 9, 10, 11 quarters with a nickel left over. So 11 and 5/25, so 11.12. Any question? That is not drawn to scale. And honestly, it should be kind of obvious it's not drawn to scale. As soon as you see that this 14 and this 11, that kind of shows you that's off a little bit. Yeah, not drawn to scale. Last scenario we're discussing. When you have a right triangle, and you have an altitude drawn from the right angle to the opposite hypotenuse. And an altitude we also know is perpendicular. Anytime you run across this scenario, it forms 3 triangles. And let's discuss those triangles. Let's call them little triangle 1, medium-sized triangle 2, which is this one here, and the whole triangle, which we'll call triangle 3. Triangle 1 and triangle 2, don't they share this angle? No? Don't they share? 1 and 3. Let's discuss 1 and 3 first. Doesn't triangle 1 and the whole triangle 3 share this angle? Don't they also both have a right angle? Since they share one angle, they both have a right angle. We know all right angles are congruent. Are triangles 1 and triangle 3 similar? And by what postulate or what theorem are they similar? Angle. They have two angles that are the same, so they must be similar. So what about angle 2, or triangle 2 now? Let's compare triangle 2 to triangle 3, the whole triangle. Don't they share this angle? Since they share that second angle there, they share this, and they both have a right angle as well. Wouldn't triangle 2 and triangle 3 be similar? Sure. And you could actually go on to make this statement, by the third angle theorem, this angle would actually be congruent to this angle would actually be congruent to this angle, and you could actually prove that all three of those triangles are congruent. All three of those triangles are similar. They all three have corresponding pieces. Let's try to identify the corresponding pieces. If you're talking about triangles 1 and 2, then I believe you would see that this is the shortest side, and that it would correspond with this, which is the shortest side in triangle 2. This in triangle 1 is the medium side, which would correspond with this in triangle 2, which is the medium leg, or the shortest leg when you're talking about a right triangle. In triangle 1, this is the hypotenuse. In triangle 2, this is the hypotenuse. Those two would correspond. Now, if you're talking about 1 and 3, it's a completely different correspondence. 1 versus 3. In triangle 1, this is the shortest side. In triangle 3, which is the whole triangle, this is the shortest side. You have a correspondence there. In triangle 1, this is the medium side, which would actually correspond with this side in triangle 3. And in triangle 1, this is the hypotenuse, which would actually correspond with this hypotenuse in triangle 3. So you've got three similar triangles. Anytime you've got that scenario to where you've got an altitude drawn in a right triangle, it splits this thing into three similar triangles. And here you see a picture of them. Triangle FGH, which was a right triangle. Thank you, guys. You've got an altitude drawn from J to G, and it splits it into these three triangles, all having similarity happening. And you see the statement here, FGJ is similar to GJH, is similar to FGH, and you can see which sides correspond. The short side, FG, corresponds with JG. You see FG and JG here. The medium side, JH, would correspond with GH over here. JH corresponds with GH. But you have, my biggest thing for you to remember, you have that correspondence. You have three similar triangles. Now let's go a step further. Anytime this happens, let me do it like this. Because that looked really confusing up there. Let me try to simplify it some. Right triangle, altitude. We're going to call this A, B, C, D. We'll call the height here E and the whole bottom F. And before we go into this, let's talk about, here's your new vocabulary word, the geometric mean. Since 6th, 7th grade, maybe even further back than that, you've talked about mean, median, and mode. Okay? The mean that you did there, mean, median, mode, the mean that you did was the arithmetic mean. To find the arithmetic mean, well, we've done it this year. When we found the midpoint, we'd use the arithmetic mean. We add the two numbers, we divide it by 2. To find an arithmetic mean, let's say you've got 3 grades, 97, 98, and a 32. Sorry, it was a tough chapter 3. You have 3 grades, and if you want to find the mean or the average of those 3, you added them and you divided by 3. That's the arithmetic mean. A geometric mean is found a little bit different. You don't add and divide, you multiply and square root. Instead of adding and dividing, you multiply and square root. If I ask you to find the geometric mean between 16 and 9. Now to find the arithmetic mean, you would add the 2 together and divide by 2. To find the geometric mean, you multiply the 2 together and you take the square root of the answer. It's the square root of 16 times 9. 16 times 9 is 144. Square root of 144 is 12. Let me remind you there is a shortcut there. Okay, reminder of the shortcut. Remember back when we were simplifying these things, square root of 20, we had to split into root 4 times root 5, and we can split that. If I'm asked to find the geometric mean between 16 and 9, can I not split that into the square root of 16 times the square root of 9? Would that be faster? That way you don't even have to worry about multiplying 16 and 9 together. The square root of 16 is 4, the square root of 9 is 3, 4 times 3 is 12. Much faster. But now that we know what the geometric mean is, let me discuss how it applies to this stuff that we're doing. You have this scenario of altitude, right triangle. Here's the rules, and I'd write these down in some way. The altitude in this triangle, the E, is equal to the geometric mean between the two bottom pieces. That means if you've got this setup, you've got this scenario, and you want to know how tall it is. If you know what those two bottom pieces are, let's say it's a 16 and 9, then you know automatically by applying this formula that E, the altitude, would be the square root of 9 times 16. Your other case, if you're asked to find the side here is going to be the geometric mean between the bottom piece that's associated with it, which is here, and the whole piece. And F there, instead of writing F, if you'd rather write B plus D, it's the same thing. The whole thing. And then your last scenario, the other side, these are the only three formulas you'll have to know. The other side, C, from what I just told you, if A is the geometric mean between B and F, C would be the geometric mean between D and F. Good. There's your three formulas. So using these formulas, you can figure out if you've got B and D, then automatically you have E. If you have the length of E, the length of B and F, what those little pieces are, you automatically have the length of A. And the same thing with C, if you have the length of D and F, you can find C. Here's your problems. Okay, first problem. You have that scenario, but to make it look better, let's do this. That's what you're used to seeing it look like. So let's spin this thing around, and let's try to find X, Y, and Z. All you're given is that this little piece is 5 and this piece is 20. Here's the three scenarios. To find the height is the geometric mean between the two pieces. This side length is the geometric mean between the small piece and the whole piece. This side length is the geometric mean between this piece and the whole piece. So let's start with X. X is going to equal the geometric mean between 5 and 20. What's the value of X? Good. Okay, second scenario. Let's look for Y. Now stop for just a second. I just found X. What I'm about to show you is not the only way to find Y. Guys, look at that little triangle in there. You have now, this is 5. I used the geometric mean between 5 and 20 to find that this was 10. What's the other method of finding Y? Thank you. Pythagorean theorem. A squared plus B squared equals C squared. You can do 5 squared plus 10 squared equals Y squared. And you can solve this with Pythagorean theorem. What I'm showing you is the shortcut. Y is the geometric mean between the small piece associated with it, this small piece here, and the whole bottom. It's the geometric mean between 5 and 25. Don't multiply that together. Because what you're about to do if you multiply that together is you're going to multiply it and then you're going to turn around and try to simplify it. Guys, that's already split the way that you need it to split. You'll see that? I know the square root of 25. So why not just go ahead and split this into the square root of 25 times the square root of 5. The square root of 25 times the square root of 5. And if you do the Pythagorean theorem now, you're going to end up with the exact same thing. Finally, Z. Z is the geometric mean between this piece and the whole piece. So between 20 and 25. And you can do the same thing there, but let me caution you about something. I see another perfect root right there. 25, I know, is a perfect root, but I see another one inside of that 20. What's a perfect root in 20? 4. Take the 4, and if you get used to what I'm showing you here, it makes these things so much easier. Take the 4 out of this and put it with this. It's now 100, and when you took the 4 out here, it's now 5. So you have the square root of 100 times the square root of 5, the square root of 100 times the square root of 5. So z is 10 root 5. So you found every missing piece in that right triangle. Again, you see it flipped upside down. You're used to seeing it worked where the hypotenuse is on bottom, but we'll leave it like this for this one. Okay. Line Z there, your Z missing is your altitude. And here's your 3 scenarios. To find Z, Z is the geometric mean between the 2 pieces. X is the geometric mean between this piece and the whole piece. Y is the geometric mean between this piece and the whole piece. That's the 3 scenarios you're looking at. So to find Z, Z is the geometric mean between 8 and 25. X is the geometric mean between this and the whole, so 8 and 33. Y is the geometric mean between 25 and 33. You can go ahead and multiply them together if you'd like. I like to split them before I multiply them just because they're easier to see now that they've already been split once. Let's simplify these down. This, if you multiply it together, that's the square root of 200. Square root of 200, you could give that as a decimal, but let's go for exact here. I noticed that if I leave it split 25 times 8 to simplify, that there's an extra perfect root here. So let's take the extra perfect root out of this and put it over here. What is, help me, Roderick, what's the perfect root located inside that 8? 4. Move that 4 over to the 25, you now have 100. That looks better. Okay, the square root of 100 times the square root of 2, the square root of 100 times the square root of 2, 10 root 2. Or you could give it as a decimal. That's going to be like 14.1 or something like that. Dylan, square root of 8 times square root of 33. Neither one of those are perfect roots. Do you see a perfect root located in either one? 4 right here. Same thing. So let's do it backwards. Let's take the stuff that's not a perfect root and move it over there. So let's leave that as the square root of 4 times, take the 2 from there, move it over here. Square root of 4 times 66. If you don't understand what I'm doing, guys, multiply that together and then try to simplify. Okay, this is simply shortcuts what I'm showing you here. 66. Does anybody see any perfect roots in 66? I don't. Square root of 4 times square root of 66. And the last one, I think this one's already split right. There's no perfect roots located in 33. That's simply 3 times 11. There's not a 4, there's not a 9, there's not a 16, 25. None of those numbers are located in here. But I do know the square root of this. So let's leave that as 5 root 33. There's all your side lengths.